Oh, hi everyone. Thank you so much for showing up for your math learning. We are taking a look at some of the important rules of math. If math were a game like chess, this stuff is like how pawns move, how the bishop moves, what your queen can do in different situations. This stuff wants to become so automatic you stop thinking about it unless someone asks you to explain it. So that's why we're going to practice today. And we're going to practice with some delta math after we complete this sheet together. So a little bit of vocabulary. An exponent, if we have this thing like 3 squared there, the 2 is the exponent. This whole thing is a power of 3, meaning it's something that you can get by multiplying 3 by itself repeatedly. Hey, if you're chatting about the cool thing that's on your phone, I'm going to be like, go see a vice principal. He doesn't hear me. Stop on your phone and talking about it as loud as I'm talking. Stop. Okay, so this is what we call a power of 3. You can achieve it by multiplying multiple copies. So the whole thing is called a power, the 3 is called the base, and the 2 is called the exponent. When we're talking about expanded form, it means take these powers of 7, there's 7 squared, there's 7 cubed, 7 to the power 2, 7 to the power 3, and write them out in that way. That's what we mean by expanded form. Okay. So overall, then we can count the number of copies of 7 that we're using there to multiply it. There's 5 copies. So we notice, what did we do with the exponents 2 and 3 to get the number 5, to get that new exponent? Yeah, we're going to add the exponents in these cases. So 9 times 9 to the 3, well, that's 9 times, well, 9 to the 3 would be 9 times 9 times 9. Oh, look, it's 9 to the 4. I can count the copies, and I can also write that as 1 plus 3. There's this invisible exponent 1 next to any number that doesn't have an exponent. Just like there's an invisible coefficient 1 next to an x. So I happen to be 45 to the 1 years old, and while that is a weird way of giving you my age, it's still true. Okay? Anything to the 1 is itself. You're basically saying take 1 copy of that thing and multiply it by 1, let's say. Okay, so then here a to the 4 times a to the 6, well, that would be a times a times a times a. That's a to the 4 multiplied by a times a times a times a times a times a. What do we got at the end of the day? A to the what? Looks like wow, everyone got real quiet. A to the power what is a to the 4 times a to the 6? Yeah, 10. 10, good. Yeah. I'm going to assume you're trolling me. Okay, so a to the 10 is 4. So we take 4, we add 6, we get the number 10. There we go. So this is not a new rule about multiplication. Exponents is different than multiplication, right? Exponents is saying how many times are you multiplying by that number, by that base. So when you're multiplying powers with the same base, okay? Notice the base is the same, the base is the same, the base is the same, the base is the same. When they're the same, you keep them and you add the exponents. Important rule. Now, I hope you'll recall that if you have 6 cookies and 6 people at the party, everyone should eat 1 cookie to share your cookies fairly. Something divided by itself is 1. And it's convenient when we create these situations because we can cancel out top and bottom of a fraction. If we have 3 copies of 3 being divided by 1 copy of 3, that's the same thing as just multiplying 2 copies of 3 together. Or in other words, 27 divided by 3 is indeed 9, which would be 3 squared. Okay, so we can still do expanded form tricks to remind ourselves how the exponent laws work. I've forgotten how the exponent laws work many times, and then I use expanded form to remind myself about how they work. So here, I want you to take your cancellation pen, get your special cancellation pen out, and do this with me. Oh, it's so much fun. It got so much easier to evaluate. Oh, wow, it's even easier to evaluate now. Hey, look at that. Super easy to evaluate. I'm left with only 2 copies of 7 upstairs, which is 7 squared. So here, we started with 5 and 3, and we ended up at 2. So what's the operation that we do there? Or you had another idea? That's fine. How do we do with the exponents in this case? That's the face I make when I die inside a little bit. But yes, that's fine. You go ahead. Yeah, we subtract them. So we do 5 minus 3 is 2. That's good. All right, 2 to the 3 divided by 2 to the 2. Well, 2 to the 3 is 8. Or in other words, 2 times 2 times 2. 2 to the 2, we expand it, 2 times 2. And then get out your cancellation pen. You want to have like this special pen that you keep in your like pocket here, just for these situations. You're excited to use it. We're left with just a 2. 2 to the 3 divided by, oh wait, simplified form. It's just 2. It's just 2. 2. Okay. So we had 3 minus 2 equals 1. But we don't necessarily need to write it. Okay, we don't need to write 2 to the 1. Because again, that would be like me telling you I'm 45 to the 1 years old. It gets weirder the more times I say it. All right, 9 to the 3 divided by 9. Oh, there's that 9 to the 1 again. What's this going to be? Let's skip over this whole expanded form step. Tell me what we're going to get. 9 to the 2, very good. 3 minus 1 is 2. Good. A to the 9 divided by a to the 6 is going to be a to the what? Good. 9 minus 6 is 3. Cool. Good. So when we're dividing powers with the same base, and again, that's important. Don't just read that and not think about what it means. If I have x to the 5 divided by y to the 4, this in no way is equal to some combination of like x to the 1, y to the 1, or something like this. No, don't. Cannot misapply this law. You can't use it when the bases are different. If they are the same, then you can subtract the exponents. Cool.
Excuse this interruption. If you want to make Black Dodge Caravan,
All right, let's carry on, everyone. So now we're looking at taking a power and raising it to an exponent. So we have 2 to the power 2. That is a power of 2. The base is 2. The exponent happens to be 2. And we're going to raise that to the power 3. One way to expand that first is to just expand this 3. So this is 3 copies of 2 squared multiplying themselves. If we expand that again, that would be 2 times 2 inside each bracket. And that's be how I would write it. There's one of the 2 squareds. There's another one of the 2 squareds. And there's another one of the 2 squareds. At the end of the day, it's 2 to the 6. So we're noticing that we had 2 and 3, and we got to 6. So what do we do to those exponents? Huh? So we definitely we multiplied these exponents by one another. We times them. That's good. 3 squared squared. This is not a great example because like 2 squared is the same thing as 2 plus 2. Is the same thing as 2 times 2. It's a weird number that way. But if we expand it once, it's 3 squared multiplied by 3 squared. And then we can expand each one of these again. So it's 3 times 3 times 3 times 3. You see how you get 2 groups of 2? And that's kind of the definition of multiplication. 3 to the 4. So here we did 2 times 2 equals 4. How about this here? Negative 3 in brackets to the power 3 in a square bracket to the power 2. Here's my suggestion. When things get weird in math, whether it's weird with the notation or weird with your instructor, just get real stubborn with applying your rules, okay? So in this case, I'm just going to do the same thing we did here with this one, with that one. And I'm going to write minus 3 to the 3 times minus 3 to the 3. Look at that. 2 copies of minus 3 cubed, multiplying one another. And then bring it over here. This is minus 3 times minus 3 times minus 3. That's one of our minus 3's to the 3 multiplied by minus 3 times minus 3 times minus 3. Look at all those copies of minus 3 multiplying one another. Okay, the base is just a little weirder. It's a negative number. Keep that and keep your notation tidy, and you'll be fine. At the end of the day, this is minus 3 to the 6, which is 729, I think. Yeah. So there we go. So we had 3 times 2 gave us 6. That's how we got that exponent. What will this one be at the end of the day? A to the 3 to the 4. There we go, expanding the 4. There's 4 copies of a cubed. What would happen if I switched gears and used my other rules here? What if I notice that I'm now multiplying powers with the same base? I recall adding the exponents here. What would we get? Yeah. We get 12 anyway, okay? It's just 4 groups of 3. It's like doing, you can do multiplication by doing repeated addition, no problem. Your 2 rules should never create a contradiction if you're applying them correctly. So this is a to the 12. We have 3 times 4. That gives us 12. Cool. So when raising powers to powers, we keep the exponents the same and multiply the exponents. So, fill in your rules here. B to the m times b to the n, that will be b to the what? What will my exponent be up there in brackets? So I'm multiplying exponents of the same base, so what do I do with the exponents? Ooh. When I'm multiplying powers with the same base, what do I do with the exponents? We add them. And if you forget, like people just did, you see how easy it is to confuse the different rules. Okay? Just notice that it's easy to confuse the different rules. So you need to go back to, okay, wait, I forget that rule. Let me use expanded form with a simple example. Create an example for yourself like that you can use to reteach yourself the rule. Expanded form is going to get you thinking about exponents in a way that will build your understanding. So here we have, if we have b to the m times b to the n, that will be b to the what? Yeah, we'd have m plus n up there in the exponent. Good. So if we do like 3 cubed multiplied by 3 to the 7, we would have 3 to the 3 plus 7. That's a fancy way of saying 3 to the power 10, which is not 30. But I don't happen to know what it is offhand. Is big. It's 81 times 729, whatever that is. What if we're dividing powers of the same base? What happens to the m and the n? This will be b to the what? Good. We're going to subtract the exponents in this case. Well applied, that rule. So we're going to subtract our exponents. Give yourself an example like 5 to the 7 divided by 5 to the 3 is going to equal 5 to the 7 minus 3 just equals 5 to the 4. Something like that. And you can create examples like these for yourselves and explore them in expanded form so that you're building your knowledge of how number work. All right, powers of a power. B to the m to the n is how that's read. B to the m to the n works out to be b to the what exponent now? Yeah, we're just going to write that as mn, because if I just write those two things together, it means multiply. So here another example, 7 to the 3 to the 11 is going to be 7 to the 3 times 11 equals 7 to the 33. which is an enormous number. You don't want to calculate it. Now, these aren't rules necessarily, but they're going to be applying our rules. Okay, so these we can also take a look at here. AB to the m, let's have an example like 3x all to the power 3. Let's use expanded form to explore this. We're going to have 3 copies of 3x multiplying itself. So I'm noticing that at the end of the day, we would have 3 to the 3, x to the 3. Okay? So when we are raising a product to an exponent, we would have this being a to the m, b to the m. The a gets multiplied by itself m times, the b gets multiplied by itself m times. So there, that actually makes a decent example. Here's another one. 5x squared y raised to the power 6 equals 5 to the 6 x to the 2 times 6, because we apply that rule, y to the 6, which equals at the end of the day 5 to the 6 x to the 12 y to the 6. Was that directed at me, or is that a question? Or is that to... No? Oh, I thought someone said what?
No.
Like something didn't make sense. Oh, cool. Okay, good. All right. A over b to the m. Well, let's explore it. Let's say we have 3 over 5 all raised to the power 2. Well, that would look like this. 3 over 5 multiplied by 3 over 5. Oh, that's just 3 squared over 5 squared. It's essentially the same thing we're seeing up here, except we have a over b to the m just equals a to the m over b to the m. That exponent is going to apply to both the numerator and the denominator. When that fraction is in brackets, the whole thing is multiplying by multiple copies of itself. So an example we might be like 3x over y raised to the power 3. This will equal 3 to the 3, x to the 3 over y to the 3. No further simplifications possible because x and y aren't the same base. What about stuff to the 0? What if I have to the power 0? Are people super quiet because you remember that this one is super tricky? It's 1. Anything to the 0 is 1 if b is not itself 0. Okay? If you have 0 to the power 0, that's just weird. I don't know how you got into that weird math situation, but just kind of pretend it doesn't exist. Okay? But if you have something non-zero, which is most numbers, to the power 0, that equals 1. And let's take a look at why that is. Okay? Let's apply our exponent laws to this situation. 3 to the 5 divided by 3 to the 5. What's something divided by itself? If I have 243 cookies and 243 people, how many cookies should everyone eat? 1. Something divided by itself must be 1, right? Must be. Okay? But I could also do this as 3 to the 5 minus 5. I can apply my exponent law there and subtract the exponents. That gives me 3 to the 0. So that's one way we can see, yes, stuff to the 0 is like saying multiply by no copies of that thing. All of your copies of that thing have canceled out. You're just left with 0. Yeah?
So,
Yeah?
there's 2 answers to that question.
But this is 1.
Oh wait,
Anything to the 0 is 1. So there's 2 different roads to get to the same place. Yeah, it's a little bit like saying, oh, I can take Oak Street or Maple Street to get to where you live. But you don't live in 2 places, you live in 1 place, right? Yeah, probably. Yeah. Or well, maybe some people do live in 2 places. Okay, and then we haven't talked about negative powers, but do people recall negative powers and what these might mean? We'll spend a little bit of time on the negative power here. Let's say I have a different situation, 3 to the 5 divided by 3 to the 7. Let's use our exponent laws. What would we have here? 3 to the what? Some kind of subtraction statement, please. What would our subtraction statement look like?
5 minus 7.
5 minus 7. What is a 5-degree day that gets 7 degrees colder?
-2.
That would be 3 to the -2. Wait, I forget what this negative exponent means. Can someone remind me what it means?
Means that you put it like it's 3 times.
What have I been saying is a really useful way to remind yourself of these rules? When you forget, what should you use?
Calculate.
Use the expanded form. You can use a calculator. And your calculator will tell you that this is 0.1 recurring, which will be a little annoying. You won't really know what to do with 0.1 recurring, okay? If you do this on a calculator, 0.1 recurring. But what we're going to get here if we use expanded form is 3 times 3 times 3 times 3 times 3 divided by 3 times 3 times 3 times 3 times 3 times 3 times 3. Get out your cancel pen. Cancel, 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 cancel. So is this equal to 0 on the top? No, Wait. No, Mr. Jennings, it's equal to 1 on the top. Right, yes, we canceled all those away and they cancel down to 1. Yes. There's an invisible multiply by 1 up there. Don't forget. So we end up with 1 on top and 2 copies of 3 downstairs. Look at that. 2 copies of 3 downstairs. Or in other words, this is 1 over 3 squared, which is the same thing as 3 to the -2. Okay? So 3 squared means please multiply by 2 copies of 3. In other words, the number 9. 3 to the -2, you can interpret the negative exponent as please divide by that many copies of that number. Division is the opposite of multiplication, in the same way that positive numbers are the opposite of negative numbers. And another way to think about it, this is my favorite way because you get to tell yourself a little story. Huh? No, it's 1/9. 1 over 9. 1 over 3 squared, 1 over 9. Which is 0.1 recurring. Okay? So another way to think about this is to say, okay, that negative exponent, it's a bossy landlord. It says, hey, 3, take all your stuff, his stuff is 2, and move. Just move downstairs. So 3 to the -2 is equal to 1 over 3 to the 2. You see how the negative exponent just moves the base and all its stuff downstairs. Okay? And if you had something like 1 over 3 to the -2, you just use bossy landlord. And you say, hey, move. Move upstairs. 3 squared over 1, just 9. Okay? So that's what that one do. So with that in mind, go ahead and dive directly into your Delta Math practice here. See if you can do the multiplication of powers here. Oh my goodness, I got to do this multiple times. I got x squared and I got x to the 3. So that's going to be an x to the 5. Wait, I just go this way. To the 5 and then come back down. 16 is going to be 16. I'm going to put that in the middle for some reason. And y to the 3 plus 4. Oh, that's y to the 7. Hey, it's not going to give the answer in that same way. It gives the 16 out front like any sane mathematician would do, but I did it in a different order because you can. You can multiply in any order. So apply your different rules in these situations. One of my favorite delta math things are mixed power problems because we get stuff like this. Look at that, we get to review quadratics, yay. So you're still gonna get some examples like this where you have to do these on some blank pages. You're going to write these out in this way, like this, so these will show up in mixed power problems. Let's take a look at one together. This is equal to 3x plus y times 3x plus y. Use expanded form here. 9x squared plus 6xy plus y squared. Here's 3xy, here's 3xy. Together those two make 6xy. Okay? Don't forget those. Okay, go ahead and practice.